is a Bulldog Rocketry about their Spaceport America entry, and I'll let you guys introduce yourself as you go. Okay, I'll get that. Oh.
Hello, thank you all so much for being here today. We are Bulldog Rocketry from the University of Minnesota Duluth. Please allow us to introduce ourselves. My name is Emma Nelson. I am a senior at UMD, and I am the current documentation and business development lead.
My name is Zach Coughlin. I'm also a senior, and I am the Chief Projects, Possibilities, and Planning Officer.
My name is Nicholas Clayman, and I'm a sophomore, and I am our Chief Financial Officer.
My name is Max Benson. I am currently a senior at UMD, and I'm going to be one of our technical advisors for next year.
My name is Gwen Lau. I'm a sophomore at UMD, and I am the Chief Operations Officer of Bulldog Rocketry.
My name is Logan Iverson. I am a junior this year, and I am the Chief Executive Officer.
Before, could you turn on your camera? And, we'll put you up on there on the Zoom meeting. And if you would like to be seen, you'll while you're speaking, you probably need to get in front of it.
Yep.
Okay, so as you can see, there are 6 of us here today. We represent a team of 45 students. However, it's very hard to fit all 45 of us on a rocket to get down here. And also, if you thought gas prices were expensive, you should try rocket fuel. So there are 12 different majors that comprise Bulldog Rocketry, everything from mechanical, civil, industrial, chemical, and electrical engineering to things like marketing, communication, and computer science. As I said, we are a student-led organization at the University of Minnesota Duluth, go Bulldogs, and we design, simulate, manufacture, test, and launch high-powered rockets, which we will be speaking to you about today. We also currently manufacture a solid rocket motor that achieves a 30,000-foot apogee, which we will also be discussing today.
All right, so Bulldog Rocketry participates in high-powered rocketry, which is classified as a rocket with a total weight of over 1,500 grams and contains a motor with more than 125 grams propellant, or 160 Newton seconds of total impulse, or uses a motor with an average thrust of 80 plus Newtons. In order to participate in high-powered rocketry, there are certain levels of certification that must be met, allowing rocketeers to fly bigger and better motors. Our team currently has 7 EEE level 1 certifications, 1 level 2, and our mentor has had his level 3 certification for over 2 decades. So the video in the middle there is an example of a level 1 certification launch. So in order to get level 1 certified, you have to build, manufacture, and launch, and then be able to recover the rocket after it has been launched. The larger and higher levels of certification have more requirements, such as a test or larger motors.
Step in front of
Camera.
Max's laptop when you speak, please, and then everybody will be able to see you too.
Now, while certification rockets can typically be between 3 and 6 feet in length, our competition rocket is usually 14 feet or longer. So some components on our competition rocket would include our electronics. Our electronics bay would include our DAVE system, which is a GPS tracker with instantaneous readout that monitors location, and it monitors for certain events during the flight of the rocket. This system works in tandem with our recovery systems to ensure a safe landing for the rocket. We manufacture our own parachute out of ripstop and shock cord, and some of our designs include elliptical, cross shapes, and we are working on certain experimental ones such as pants.
Now the most visual aspect of our rocket is the airframe, which is basically everything that you see here. Everything of this airframe is student researched and developed and is built in-house. Some aspects or some components of our airframe are our fiberglass nose cone, carbon fiber body tubes, fiberglass electronics bay, and our aluminum motor tube. Inside of our airframe holds our payload. Now, essentially what a payload is the whole reason why I sent up a rocket in the first place. Often it's something that ends up in space, but for us, it goes up to 30,000 feet, which is our apogee or our highest point that the rocket travels. For Bulldog Rocketry in the past, we've made such payloads such as a glider, an airbag recovery system, a camera that can detect life on Earth, and currently we are working on a payload that will be able to land vertically. Additionally, within our airframe is our motor, which happens to be the most fun aspect of our rocket, I believe. Our motor, again, is student research and developed under our mentor, Dave Weiniger. Our motor is manufactured and then is tested using live static fires. Really fun to see. And if you would like to see that, we are having an exhibit later today at 2 that you can come watch those videos. It's a lot of fun. You can be there.
We're going to be talking to you about 2 competitions that Bulldog Rocketry has a lot of experience in today. First one being the Midwest High Powered Rocketry Competition, hosted by the Minnesota Space Grant, and the second being the Spaceport America Cup down in New Mexico, hosted by the Experimental Sounding Rocket Association. First one, Midwest High Powered Rocket Competition, is hosted every year down at the Tripoli launch site in North Branch, Minnesota. And something cool about this competition is that every year they have a different challenge that competing teams need to meet. So Bulldog Rocketry, we competed in this for 5 years from 2013 2017, and we had particularly successful launches in the boosted drag, active drag, and adaptable rocket competitions. So the boosted dart competition was to build a 2-stage rocket. The adaptive drag competition was to have an onboard drag control system so that on the ground,
Todavía la grabación necesita 12.
sorry about that. Oh, no worries. Yeah, so the active drag competition, that was to kind of control the altitude of the flight from the ground using an onboard drag manipulator. And then the adaptable rocket was to build a rocket that would be launched twice with 2 separate motor classes and have it reach the same altitude both times. This year, after a long pause on the competition of being hosted in person because of the global pandemic, they're having the theme of returning to flight. And this competition is going to be a really cool one because teams will build 3 to 8 rockets that are supposed to differ in as many ways as possible. So if you can make it down to the competition in May, I highly encourage it. I think it'll be one of the coolest launches in a while.
Currently, since 2018, we've been competing in the Spaceport America Cup hosted in Las Cruces, New Mexico in the middle of June. And what this competition is comprised of is there's many different categories where teams can compete in individually and then within their own categories and then as well as a whole overall. And so some of these categories are based on altitude. So the minimum altitude that you can kind of shoot for is 10,000 feet, or what we've been going for over the last 5 years, which is the 30,000 foot category. But you can also vary what kind of motors you're going to use or what kind of rockets. So we compete in a student research and design, or SRAD, solid propellant, but there's also opportunities for hybrid and bipropellant liquid systems, which are deemed kind of more experimental. And then there's also opportunities there for some more of these experimental launches, as well as if you're interested in doing a high altitude attempt. Some of those are going along as well. So if you're looking to reach altitudes of closer to like 100,000 feet, or I believe their waiver also goes up to the Kármán line, which is the edge of space, or 330,000 feet. And in order to reach these altitudes, like we mentioned earlier, we're having to build much larger rockets, which puts us on the scale between 14 feet and I believe our largest rocket in 2018 was just under 20 feet at 19.5 feet or so, which housed our 6-foot carbon fiber glider, which is another aspect of this competition, which is the payload, like Logan mentioned earlier. And so if we have a little bit of time, yeah, it looks like it. Just to kind of give you an idea of what this competition actually looks like down in person, there's a 14-minute documentary that was put together in 2019. This is just a 1-minute trailer, but it does a good job of kind of showcasing what all goes on at this event.
For rockets, it's either I want to see it explode or I want to see it work perfectly. Nothing in between because it's cool either way, right?
I just pray that everything goes as planned because we worked all year for 60 seconds, essentially.
So we are competing against teams that are funded by their governments. They're given these resources that we don't have. When you're given such a small budget, you're forced to be creative.
These students are very resourceful. They're a scrappy bunch.
I was the kid growing up who wanted to be an astronaut. I was actually able to create a first robotics team at my high school because we really didn't have engineering experience there.
For me personally, growing up in a broken home restricts you from getting this far. I never thought I was capable of being an engineer.
All right, thank you so much for coming and listening to us today. What questions do you have about Bulldog Rocketry, high-powered rocketry, or the intercollegiate rocket engineering competition?
How close to the 40,960 NSEC mark is your O motor?
I believe we're close. In 2019, I believe we tested it and it was a 99% O, so it was just under that mark. Last year in the spring, we were closer to I want to say it was closer to a mid-90s, low to mid-90s, just with a little fluctuation in our material, it seemed. But our simulation still showed us getting around just over that 30,000 foot mark.
And when does it reach max velocity per second?
Our max velocity occurs at, I want to say between 8,000 and 10,000 feet.
Okay.
So our max velocity is Mach 1.5, which it's like 1,100 miles per hour or something like that. I don't know, remember. Yes.
What exactly on the rocket is made out of composites?
So we manufacture our body tubes. So the stuff that houses our parachutes, our electronics, we use both carbon fiber and fiberglass components, depending on some of the design criteria. For example, our electronics bay and our nose cone house electronics that need to send RF signals, which aren't able to pass through carbon fiber as effectively. And so we use, so if we go like back to this picture. Perfect. The majority of our, like the visible sections are made out of composite materials. So everything between here is essentially made out of either fiberglass or carbon fiber, and then connected with aluminum couplers with bolts, and depending on where our separation points are, we use nylon shear pins. Yes.
Do you have live radio contact with the rocket while it's flying?
Yes. So we've had 2 systems that we've used for live readouts. It's the Kate and then our own student research model, which was the Dave that we mentioned earlier. And so both of these they'll give out like altitude updates for us. So it'll read out like 10,000 feet, 15,000 feet as it's going up. And then as our different deployments occur, so like rockets reached apogee, main parachutes or drogue parachutes deployed, main parachutes deployed, rockets on the ground and ready to be collected. Those sorts of events are all communicated through the systems.
What about the ground antenna? How does it know, how to point the antenna out of the rocket?
We just use a handheld. It's generally within, I think it was within 2 miles or so. And so I don't remember us having an issue. When it's on the ground, we have trouble with it or receiving live packets from our systems. And so we'll just use close. So as it's falling, so as long as it's above ground, we should still be getting signals from it. But we don't have an active like tracking system yet, at least. Yes.
It's hard to tell, is that nose cone like a conical, a carve and a hack? What is?
Our nose cone is a three-quarter power series nose cone, so it follows that path along the whole profile of it. I don't know if there's any other technical term for it.
Well, yeah, just it's a 3/4 power series and it has a fineness ratio of 5, which I believe it's the diameter to the length ratio.
All right. Well, thank you very much.